Let's study dynamical friction, which is a major process occurring in stars and galaxies that doesn't happen with planets in planetary dynamics. Consider endpoint masses of mass mi moving with velocities vi. They're moving in a system, let's call it a galaxy, of radius r and mass m. The potential that a particle sees as it moves through the system has two components. So this is the potential. It has a smooth potential, that's the red curve, which is due to the mass of all of the objects. This potential is a cumulative effect of all of the masses in the system. And it has short and strong fluctuations due to discrete objects. Now, these fluctuations are produced by encounters with individual objects or collisions. There are a number of effects related and produced by the encounters. One of them is two-body relaxation and scattering. What do we mean by this? We expect that there should exist a gradual accumulation of deviations of trajectories of particles. Here you see in the black solid line the unperturbed trajectory that a star would have in a smooth potential, whereas the blue dashed line here is showing the real trajectory that slightly deviates from the unperturbed path due to discrete encounters with other stars and other objects in the galaxy. And the time scale for the accumulation of these perturbations in the path is called the two-body relaxation time. Now, there are different ways to characterize the deviations, but all of them treat the deviations in a statistical way. For instance, we can define the relaxation time as a time when the average deviation of the velocity is equal to the velocity of the unperturbed motion. Another measure of deviations is the deviation of the energy of the particles. In order to find the time scale for the effect, we estimate the local rate of change of the deviations. For example, if we use velocities, then the time scale of the two-body relaxation is given by this equation. Delta V over V is equal to delta T over the relaxation time, where delta V is the change in the velocity V in the time interval delta T. Now, more massive objects moving in the galaxy, they experience a drag and their motion is slowed down. This effect is called dynamical friction. The effect is illustrated here. You have a mass that is moving through a sea of stars. Stars are being displaced in the wake of the massive object. This object is moving, and as it moves, it is attracting stars. Because the object is moving faster than the acceleration that it imparts on stars, it's going to take some time for the stars to move. The massive object will have passed, and then what happens is that the density of stars, the number density of stars in the wake, is bigger than the number density of stars elsewhere. So this wake here, this enhanced wake, is going to exert a force, a gravitational force, on the object. This force acts just like a drag force if you had a marble that is traveling through honey. This drag is going to slow down the object as it travels through. Now, due to the drag, a massive object loses energy and angular momentum and gradually sinks to the center of the system. For instance, here we see the decay of the orbits of the Magellanic clouds around our galaxy. The upper curves here show the radius of the clouds from the galactic center, the thick lines for the large Magellan cloud and the thin lines for the small Magellan cloud. The dashed curve here shows the separation between the large and the small Magellan clouds. As you see, because of dynamical drag, the orbits are sinking and eventually they'll merge with the Milky Way. In this model, the clouds will merge with the Milky Way in about 6 billion years. Yet this model here is unrealistic beyond 3 billion years in the future, because the Milky Way will experience a much more violent merger with the Andromeda galaxy. Opposite to drag is dynamical heating. If some object is slowing down their motion, then other objects will accelerate, will heat up, which is a process that in some cases leads to evaporation. In fact, some objects may escape from the system and become unbound. The process of slowing down massive objects and accelerating lighter objects leads to two main results. One is a tendency of equipartition of energy. If we have that the masses m1 and m2 are such that m1 is smaller than m2, and m1 gets accelerated while m2 gets slowed down, then the kinetic energies are going to get closer to each other. The second process is mass aggregation. If the objects sink depending on their masses, if the massive ones sink to the center and the less massive ones evaporate, then you have that the distance to the center for the more massive objects is going to be smaller than the average distance to the center of the smaller objects. This process is seen in globular clusters.